In view of the ever-growing list of confusing discoveries being recorded by the James Webb Space Telescope, JWST, it's becoming increasingly clear, especially to Nobel Prize-winning physicist Adam Rees, that our understanding of the universe is far from complete. Rees and his fellow astrophysicists are grappling with a cosmic conundrum: the universe is not behaving the way our best theoretical models predict. Specifically, it's expanding at a rate much faster than it should, given what our current cosmological framework tells us. This phenomenon is referred to as the Hubble tension, and it represents one of the most pressing mysteries in modern astronomy. However, researchers from the universities of Bonn and St. Andrews believe they may have discovered the underlying reason behind this puzzle. The catch? Their proposed explanation directly contradicts the long-standing gravitational theories laid out by Isaac Newton and Albert Einstein. The James Webb Space Telescope is truly revolutionizing our view of the universe. Ever since its deployment, it has unveiled astonishing and sometimes troubling data, appending long-held assumptions in astrophysics. One of its most perplexing findings has been the detection of early galaxies that appear far too massive for their place in cosmic history. These galaxies seem to have formed just a few 100 million years after the Big Bang, yet their size and structure rival those of mature galaxies in the modern universe. According to our standard cosmological model, such early formation of massive galaxies simply shouldn't be possible. However, a new study proposes a different interpretation of these redshifted objects. The researchers argue that many of these galaxies may not be galaxies at all, but rather growing supermassive black holes. The intense radiation observed is likely not from countless stars, but from material falling into these monstrous gravitational wells. If this hypothesis holds up, it would imply that these early cosmic objects are significantly smaller and lighter than previously believed. That, in turn, would mean they do not fundamentally contradict our current models of galaxy formation. While this new explanation offers some relief, it still raises several important questions and demands further observational follow-up. Nonetheless, we might be inching closer to solving what initially appeared to be a universe-breaking mystery. Sadly, the same cannot be said for the problem of cosmic expansion. The Hubble tension remains unresolved, and arguably more confusing than ever. To understand the depth of this issue, we must look back about a century. The roots of the Hubble tension trace back to Edwin Hubble, who not only discovered that the Milky Way is not the entirety of the universe but also that galaxies are receding from us. This revolutionary observation led to the idea of an expanding universe, a concept that eventually culminated in the Big Bang theory. Initially, the expansion was thought to be slowing down under the influence of gravity. But in the 1990s, observations of distant supernovae shocked the scientific community by showing that the rate of expansion is not slowing down, it's accelerating. This prompted the introduction of a hypothetical force called dark energy, an uncharted and mysterious component of the universe that supposedly counteracts gravity on cosmic scales. But this leads to a crucial and deceptively simple question: how fast is the universe actually expanding? The expansion rate is quantified by the Hubble constant, and it is here that the tension arises. According to the standard cosmological model, which draws from the cosmic microwave background and large-scale structure of the universe, the Hubble constant should be around 67 km per second per megaparsec, km/s/mpc. For context, 1 megaparsec is roughly 3.26 million light-years, and 1 light-year is about 9.46 trillion kilometers. So, a value of 67 km per second per mpc implies that for every 3.26 million light-years of distance, galaxies are receding 67 km per second faster, an astonishing 241,200 km per hour per megaparsec. However, direct astronomical measurements tell a different story. Observations using techniques such as supernovae distances, red giant stars, variable stars, and gravitational lensing consistently yield a higher value, approximately 73 km per second per mpc, or 262,800 km per hour per megaparsec. This difference of around 6 km per second per mpc may seem minor, but in cosmological terms, it's massive, translating to a discrepancy of about 20,000 km per hour. This unresolved contradiction between theory and observation is what scientists now call the Hubble tension. One might assume that the discrepancy could stem from measurement errors, either in the theoretical models or in observational techniques. To investigate this possibility, Adam Rees and his team turned to the James Webb Space Telescope. Their goal was to re-examine the data originally gathered by the Hubble Space Telescope, this time using Webb's more advanced infrared capabilities. Over the last 2 years, Webb has collected vast datasets on distant galaxies and cosmic markers, which Rees's team meticulously analyzed. Unfortunately, the results didn't resolve the tension. In fact, they confirmed it. Webb's most extensive analysis to date also yielded a Hubble constant of 72.6 km per second per MPC, further validating the discrepancy rather than refuting it. Adam Rees summarized the significance of this result succinctly: the discrepancy between the observed expansion rate of the universe and the predictions of the Standard Model suggests that our understanding of the universe may be incomplete. When both Hubble and Webb, the flagship telescopes of NASA, arrive at the same result using different observational methods, it's a signal that the problem runs deep. According to Rees, this challenge is also an unprecedented opportunity. He speculates that the true cause could be an exotic form of dark energy or dark matter, a fundamental error in our understanding of gravity, or even the presence of a new, undiscovered type of particle or field. Speaking of gravity, this is where things get even more interesting. A bold new hypothesis from researchers at the universities of Bonn and St. Andrews might offer an entirely different solution. They suggest that gravity itself may not behave the way Newton and Einstein envisioned. According to their new model, the Milky Way might be located within a supervoid, a vast, underdense region of space. To grasp this idea, consider the large-scale structure of the universe. Galaxies are grouped into clusters, which in turn form larger structures called superclusters. These structures are arranged in a cosmic web, where dense filaments of matter enclose enormous bubbles of relatively empty space, known as voids. The idea that our galaxy could be embedded in such a void isn't new, but this latest study, led by Sergei Magino, provides compelling simulation data to support it. The researchers compare the situation to an air bubble trapped in a cake. Just as the bubble is surrounded by denser material, a cosmic void would be surrounded by regions of higher matter density. The gravitational pull from these denser regions would draw nearby galaxies outward, making them appear to accelerate faster away from us, an illusion created by our position within a low-density region. If correct, this local underdensity could explain the anomalously high Hubble constant values derived from local measurements. The void would cause galaxies to appear to be receding faster than they actually are on a universal scale. But this theory, too, comes with a significant caveat: the Standard Model of cosmology does not allow for such large, underdense voids to exist in the first place. Matter, according to current theory, should be fairly evenly distributed across the cosmos. Yet, observational evidence suggests otherwise. Another research group has found galaxies about 600 million light-years away that are moving away from us 4 times faster than the Standard Model would permit. This lends credibility to the idea that our cosmic neighborhood is far from typical. One of the researchers involved, Pavel Kropa, believes this discrepancy might point to a more fundamental issue: our understanding of gravity may need to be revised. To test this, the team used a modified theory of gravity known as MOND, short for Modified Newtonian Dynamics. Developed in the 1980s by Israeli physicist Mordechai Milgram, MOND alters the equations that govern motion and gravity, eliminating the need for dark energy. Intriguingly, this model not only explains galaxy rotation curves without invoking dark matter but also predicts the existence of massive voids in the universe. If gravity operates as described by MOND, then the Hubble tension would vanish entirely. The observed discrepancies would no longer reflect conflicting expansion rates but instead point to variations in the distribution of matter caused by modified gravitational behavior. However, embracing MOND would mean rejecting fundamental tenets of Einstein's general relativity, a seismic shift in theoretical physics. It remains to be seen whether MOND or similar alternatives can stand up to rigorous scrutiny across all cosmological scales. But if these modified gravity theories are validated by further observations, it could mark the beginning of a new era in our understanding of the cosmos. Subscribe to Space Lab, your portal to the wonders of the universe.